Good evening. I am Antik Ganguly from India Institute of Technology. Today we will be studying about the generalized constants of transmission line. We know that transmission lines are required to transfer power from one point to another, specifically from the generating station to the consumers. Now here we can see a transmission line single line diagram where you can see that this is a generating station from where a step-up transformer is being used, which is called a generating transformer, to transfer power through the transmission line to a substation where the power is again being the voltage is being stepped down and it is being supplied to the customer. Now the performance of the transmission line depends upon the transmission line parameters. We know that there are some electrical parameters such as resistance, inductance, capacitance and admittance, which conductance or admittance, which can be used to find out the equivalent circuit of the transmission line. This is the equivalent circuit of the transmission line. This is the equivalent circuit of the transmission line, where you can see the sending end voltage here. This is the sending end current, the receiving end current, and the receiving end voltage. So we can say that this is the sending end and this is the receiving end. So power is being transferred from the sending end to the receiving end. The entire transmission line in between can be modeled using these elements, where resistance is the unit of resistance is ohm per unit length, the unit of inductance is Henry per unit length, the unit of capacitance is farad per unit length, and the unit of conductance is mho per unit length. Now this unit length is generally 1 kilometer depending upon the transmission line, but it can vary from case to case. Now, what are ABCD parameters? The ABCD parameters are generalized constants or generalized circuit constants which are used to model transmission line. The ABCD parameters are used to model transmission lines in a two-port network linking the input and output voltages and current. As in the previous diagram, we have seen that this is the sending end and this is the receiving end. In the next diagram also, we can see that we have got a sending end and we have got a receiving end. But the equivalent circuit of the transmission line is represented as a two-port network, where inside this there is the equivalent network. Okay. Now this is a four-terminal two-port network, where this is the PQ is the sending end terminal and R and S is the receiving end terminal. These ABCD parameters are required to provide the link between the supply and receiving end voltage and current. It is required to electrically model the transmission lines and understand the performance of the transmission lines based on the variation of these parameters. Now, in the previous diagram, we have seen that we have got inductance, resistance, capacitance, and conductance. We can say that the impedance of the transmission line is R plus J XL. Okay, where XL is nothing but omega L and the admittance is Y, which is G plus J omega C. This is the impedance of the transmission line, that is Z, and this is the admittance of the transmission line, that is Y. Now, when we come to the ABCD parameters of the transmission lines, we can see that we can represent the receiving end parameters, which is VS and IS, in terms of the we can represent the sending end voltage and current with respect to the receiving end voltage and current using the values of A, B, C and D. Now what is A? A is nothing but the open circuit reverse voltage transfer ratio, which is unitless. So A is Vs by Vr when IR is equal to 0. What do we mean by IR being 0? That means the receiving end side is open circuited. The receiving end side is open circuited and then there is no current flowing through that circuit and so IR is 0. Similarly, we can find B is equal to Vs by IR, where B is nothing but the short circuit reverse transfer impedance that is represented in ohms. The unit of B is ohm. Here the receiving end voltage is 0. The meaning of the receiving end voltage being 0 is that the receiving end side is short circuited. So, if we draw the diagram of the two-port network, if we draw the diagram of the two-port network, with this being the sending end and this being the receiving end, we can say that if this circuit is not closed, then it is open circuited and this open circuit is used to find the values of A and C. Now if this receiving side is short circuited like this, then we use this configuration to find out B and D, where C is equal to A and B we already know. C is equal to the open circuit reverse transfer admittance, which is represented in Siemens, and D is equal to short circuit reverse current transfer ratio, which is again unitless. Now some characteristics of this is that A will be equal to D and AD minus BC will be equal to 1. Now we can relate these ABCD parameters in terms of voltage transfer ratio, impedance, admittance and current transfer ratio to our equivalent circuit, where we can also see that this equivalent circuit can be represented as Z. Okay, so Z is equal to Z plus 2, sorry, Z by 2 plus Z by 2. So the total impedance of the line, the total transfer impedance of the line is Z. Here it will be Y, this portion will be Y. So that is the transfer admittance. And obviously IS, IR, VS and VR we already have got, which is used to find out the reverse voltage ratio and the reverse current ratio for the ABCD equivalent circuit. Okay. Now to apply these parameters, to use these parameters to find out the characteristics of the transmission line, we need to know that what are the different types of transmission line. So the types of transmission lines can be divided into short, medium and long. The short transmission line has a length of less than 80 km. The medium transmission line has a length between 80 km to 250 km and the long transmission line has a length above 250 km. Now, when we find out the ABCD constants for a short transmission line, this is our equivalent circuit diagram, or this is our equivalent circuit diagram for the short transmission line. Here we can see that we have got the sending end and we have got the receiving end. Okay, we have got VSIS, VRIR, but we only have the impedance here. There is no admittance in this circuit. The reason of no admittance being there in this circuit is that for the short transmission line, we ignore the capacitance of the line. Why do we ignore the capacitance of the line? Because the main effect of the line capacitance is to draw charging current. In the short transmission line, the charging current drawn by the line capacitance is so negligible that we can assume that it is non-existent. So, making that assumption does not affect the calculations very much. To simplify our calculations, we ignore the line capacitance and we only consider the line impedance to calculate the ABCD parameters. Now, in this circuit, we can represent Vs as the summation of VR and the line voltage drop, which is given by Z into IR. And as it is a series circuit, we can say that Is is equal to IR. Now, if we compare these equations with the two-port network equations, which is Vs is equal to AVR plus DIR and Is is equal to CVR plus DIR, we can say that comparing this equation with this equation of Vs, we can say that A is equal to 1 and B is equal to Z. Similarly, by comparing the equations of Is on both in both this representation, we can say that C is equal to 0 as VR is not present in this equation. So obviously C is equal to 0 and D is equal to 1 as Is is equal to IR. So we can represent this particular equation of Is as Is is equal to 0 into VR plus 1 into IR. Okay, from here we can see that C is equal to 0 and D is equal to 1. So this is the value of the ABCD parameter for a short transmission line. Now we come to the medium transmission line. The medium transmission line can be represented in two parts, in two types. One is the T-type representation and the other is pi-type representation. Here we can see a T-type representation. Now, in the T-type representation, the entire impedance is divided into two parts and the total admittance is lumped in the middle. Now, from this circuit, we can say that Vc is equal to Vr plus Z by 2 into IR, which we can represent in this form because we can say that IC is equal to Vc into Y. This is the voltage. Vc is the voltage across the shunt admittance, and IC is equal to Vc into Y. So by replacing the value of Vc in the place of Vc into Y, we can get IC is equal to Vr plus Z by 2 IR whole multiplied by Y, which we get, from where we get YVR plus YZ by 2 into IR. Again, we see that Is is equal to the summation of IR plus IC, where we can write it as IR plus, we can replace the value of IC by the value that we have already obtained, So the value of IC is YVR plus YZ by 2 into IR. So we replace IC by its value, which is YVR plus YZ by 2 IR. And so we get IS is equal to YVR plus 1 plus YZ by 2 IR. Similarly, we can write VS is equal to VS is equal to VC. VS is equal to VC plus Z by 2 into IS. Okay. Now the value of VC you already know. The representation of VC we know in terms of VR and IR. VC in terms of VR and IR is VR plus Z by 2 into IR. So here we replace the value of VC by the equation that we have got. So VC is equal to VR plus Z by 2 into IR. Then we have got Z by 2 into IS. Also, we have already obtained the value of IS here, which is YVR plus 1 plus YZ by 2 whole multiplied by IR. Right? So Z by 2 and then replace IS by the obtained value, which gives us the final formula of VS, which is equal to 1 plus YZ by 2 into VR plus Z into 1 plus YZ by 4 into IR. So we have got the two sending end side equations, VS into VS and IS, where VS is represented by this equation. VS is represented by equation number 1 and IS is represented by equation number 2. Now if we compare these equations with the previous equation, where we have got VS is equal to AVR plus VIR and IS is equal to CVR plus DIR. By compare these equations of VS and IS, we can see that A is 1 plus YZ by 2. Also we know that A is equal to D. So here this is D. So comparing the equations of IS, we get that this is D. So D is also 1 plus YZ by 2. So D is also equal to 1 plus YZ by 2. So A is equal to D condition is satisfied. Again, if we compare VS, this VS with the VS that we have obtained, then D is equal to Z into 1 plus YZ by 4, and comparing IS between these two equations, we can say that C is equal to Y. Okay, so we have obtained the ABCD parameter values of T-type medium transmission line. In the next class, we will continue with finding out the ABCD constants for pi-type medium transmission line. Today, we conclude at this point. Thank you.